Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. Today we will study this very important topic with the title of Differentiation Rules. In the previous section, we learned how to find the derivative of the function by using the definition of limit. Today we will study some rules that will help us to find the derivative of the function very quickly. So the first rule here is the derivative of a constant function. If f has the constant value, f of x equals c, then df by dx equals d by dx of c, which is, according to the rule, equivalent to 0. As an example, if the function is, for example, f of x equals to any number, any constant number, like f of x equals to 5, then the derivative of this function, d by dx, f of x. See the notation that I'm writing here. It doesn't mean that d is a symbol multiplied by f of x, and here we have d also multiplied by x. No, this is a notation to denote that the derivative of the function. So df of x by dx means the derivative of the function f of x with respect to the variable x equals 0. Why? Because f of x is a constant function. So for any constant function, the derivative is equivalent to 0. The other rule is called the power rule. So if n is a real number, then d by dx of this function x to the power of n equals n multiplied by x to the power of n minus 1 for all x where the powers x to the power of n and x to the power of n minus 1 are defined. If you observe this rule carefully, the power here n is written in front of x, which means has to be multiplied by x, and the power of x now is reduced by 1. So it becomes n minus 1 instead of n. As examples here, let's see the derivative of the following functions. The first function in part A is x to the power of 3. So the solution is here. The derivative of this function is 3 multiplied by x to the power of 3 minus 1. See, 3 here is the power of x. We write it in front of x, and then we subtract 1 from the power of x. Always we subtract 1. So it becomes 3 times x to the power of 2. Now, question B, we have this function, f of x equals to x to the power of 2/3, 2 by 3. So its derivative will be 2/3 multiplied by x to the power of 2/3 minus 1. So 2/3 minus 1 is minus 1/3. So the final answer will be 2 by 3 multiplied by x to the power of minus 1 by 3. The next function in part C is x to the power of square root of 2. Again, we have to apply the same rule, which is the answer will be square root of 2 multiplied by x to the power of square root 2 minus 1. And this is for all the rest of the functions here. In part D, E, and F, we'll apply the same rule, which we call it the power rule. Now, the next rule is the derivative constant multiple rule. So if u is a differentiable function of x and c is a constant, then the derivative of c times u, c is a constant and u is a function of x, then its derivative will be c outside the derivative multiplied by the derivative of u. Don't say that because here we have c, then the derivative is 0. No. The derivative will be c, the constant, multiplied by the derivative of the function u, du by dx. As an example, if we have this function 3 times x squared, so its derivative will be 3 multiplied by the derivative of x squared, And if we apply the power rule for the function x squared, then its derivative will be 2x. So the final answer will be 3 times 2x, which is 6x. Another example is the derivative of minus u. Minus u, we can write it as minus 1 multiplied by u. Hence, minus 1 is the constant, and then we differentiate u. The derivative of u with respect to x will be du by dx. Then the answer will be minus du by dx. The next rule is the derivative sum rule. So if we have two functions, u and v, and both of them are differentiable functions of a variable x, then their sum, u plus v, is differentiable at every point where u and v are both differentiable. At such points, the derivative of their sum, d by dx of u plus v, equals to the derivative of the first function, du by dx, plus the derivative of the second function, dv by dx. As an example, if y is equivalent to x to the power of 4 plus 12x, see here we have two functions added together. Then the derivative of the function y, which is the sum of these two functions, will be the derivative of the first function plus the derivative of the second function. So if you call the first function u of x equivalent to x to the power 4, and v of x is equivalent to 12x, then you have to differentiate the first one, and you have to differentiate the second one, and add the derivatives together. So dy by dx will be the derivative of x to the power of 4 plus the derivative of 12x. And if you use the power rule, you can find the derivative of the first function, which is 4x to the power of 3. And if you use the constant multiple rule, then the derivative of the second function will be 12 times dx by dx, which is 1. And the final answer will be 4 times x to the power of 3 plus 12. Now, excuse me. Now find the derivative of this polynomial function, y equals x to the power of 3 plus 4 by 3x squared minus 5x plus 1. You can see this function is a sum of 4 functions. So the derivative of this function will be found by finding the derivative of each of these 4 functions and add the derivatives together. So the derivative of the first function will be 3x squared using the power rule. The second function will have a derivative of 4 by 3 multiplied by 2x. So we have used here the power rule and the constant multiple rule. The second or the third function has a derivative of minus 5 because we used here the constant multiple rule. And the last function, which is 1, has a derivative of 0 because this is a constant function. So if you add these 4 terms of derivatives together, you will get the final answer, which is 3x squared plus 8 by 3x minus 5. Let's see this example. Does the curve y equals to x to the power 4 minus 2x squared plus 2 have any horizontal tangents? If so, where? So here we have to answer this question, whether this function y has any horizontal tangent. Well, the horizontal tangents, if any, occur where the slope dy by dx is 0. You learned in the previous sections the relation between the derivative of the function and the slope of the tangent line to the curve of the function. And we said the derivative of the function equals to the slope of the tangent line to the function. And we know also that the horizontal line has a slope of 0. So the question here asking us, is this function has any horizontal tangent? So for this function to have any horizontal tangent, its derivative must be 0 at a certain point. So if the derivative of this function is equivalent to 0 at one point, it means that the slope of the tangent line at that point is 0, which indicates that this tangent line is a horizontal line. So to answer this question, what you need to do is you need to find first the derivative of this function y. So by applying the rules which we learned just now, you need to find the derivative of each of these three functions and add them together. When we say add, we include the addition and subtraction. So the sum rule is applied for addition as well as for subtraction of functions. So the derivative of the first function is 4x to the power of 3, and the derivative of the second function is minus 2 times 2, that is minus 4 times x to the power of 1, and the derivative of 2 is 0. So the final answer of the derivative of the y function will be 4x to the power of 3 minus 4x. Now, we need to solve the equation if this term, which is the derivative, is equivalent to 0. And then you find the values of x at which the derivative is 0, i.e., we are finding the values of x at which the slope of the tangent line is 0. So 4x to the power of 3 minus 4x equals 0. If you factorize the left side, you will get 4x in front of a bracket has x squared minus 1. The right side is 0, and the solution of this equation is either x equals 0 or x equals to plus or minus 1. So there are three values of x where the derivative of the function equals to 0. These values of x are 0, 1, and minus 1. So we will say that the slope of the tangent line will be 0 at three different values of x, which are 0 and 1 and minus 1. Hence, at these values of x, there are three horizontal tangent lines to the curve of the function. To identify the location of those points, you need to find the value of the function at each of these x values. So when x equals 0, you substitute it in the function of y. And if you put here x equals 0, if you substitute x equals 0 and x equals 0, you will get y equals 2. Then you will get the first point with the coordinates of 0 and 2. And then to find the second point where the function or the graph of the function has a horizontal tangent line, you have to substitute x by 1. So again, if you substitute in this function y equals 1, you will get a value of 1. So this is the second point with the coordinates of 1 and 1. And if you substitute x by minus 1, you will get a value of y equals to 1 also. So these are three different points where the function assumes tangent lines, horizontal tangent lines. If you look at the figure to the left here, figure 3.11 from your textbook, you will notice here, this is the graph of the function, which is the blue colored one. And at these 3 points, this is the first point to the left, minus 1, 1. And this point in the middle, 0 and 2. And this point to the right, which is 1 and 1. See the tangent line, the red colored one, is a horizontal line. So because their slopes is 0, and the derivative of the function at these 3 points is equivalent also to 0. Also, always try to correlate the slope of the tangent line to the derivative of the function. The next rule is the derivative product rule. If u and v are differentiable at x, then so is their product uv. And the derivative of this product u times v is equivalent to the derivative of the function u, is equivalent to the function u multiplied by the derivative of the next function, which is dv by dx, plus the derivative plus the second function multiplied by the derivative of the first function, v du by dx. So it's not equivalent to the derivative of the first function times the derivative of the second function. No, you have to follow this rule exactly. So you multiply the first function by the derivative of the second function plus the second function multiplied by the derivative of the first function. As an example here, if we have y equals x squared plus 1 in one bracket and x to the power 3 plus 3 in the second bracket, and these two brackets are multiplied by each other. So if we call the first bracket function u, and if you call the second bracket function v, then the derivative of y will be found by following the above rule. So we have to multiply, see this is u, function u, multiplied by dv by dx. Because the derivative of the second function is 3x squared. The derivative of 3 is 0. So we used here the power rule and the constant rule. So the derivative of the second function is 3x squared plus the second function, this is v, multiplied by du by dx, the derivative of the first function. The first function is the terms inside the bracket. Its derivative is 2x because the derivative of 1 is 0. So this is the derivative of the whole function y. And then you need to expand these brackets. You will get these terms, 4 terms. And then you collect the like terms. You will get the final answer as 5 times x to the power of 4 plus 3x squared plus 6x. Okay? So this is the way we solve such a question, by using the product rule. However, there is another method of solving this equation, might be easier way, avoiding using the product rule, which is we can first expand these two brackets, multiply out these two brackets before finding the limit, before finding the derivative. So if you multiply these two brackets together, we still in the function y, we did not calculate the derivative of y yet. So if you expand these two brackets, multiply out these two brackets, you will get these functions. And now if you differentiate these functions by using the power rule and the constant rule, you will get the same answer. Okay? This method of solving the question looks simpler than the previous one by using the product rule. Now the next rule is the derivative quotient rule. So if we have u and v as differentiable functions at x, and if the function v of x is not equivalent to 0, then the quotient u by v is differentiable at x, and its derivative is given by this formula. So the derivative of u by v is equivalent to, you have to be careful here and you have to remember this formula. So u square the denominator, see the function v in the denominator, in the derivative will be squared, and in the numerator here you multiply denominator multiplied by the derivative of the numerator minus the numerator multiplied by the derivative of the denominator. So you have to remember this. So to apply this rule, let's see this example. If y equals t squared minus 1 divided by t to the power 3 plus 1. So to find the derivative, first we have to square the denominator. So this denominator here is squared. You can see here we squared it. And then we multiply the denominator by the derivative of the numerator. See, this one is the derivative of the denominator, this d by dx, okay, which is 2t minus, the minus sign should be in front of the denominator. That's why here we use the bracket, because minus multiplied by the denominator function. The denominator function is t squared minus 1, so we have to write it in bracket, multiplied by the derivative of the denominator. So this is the numerator minus the numerator multiplied by the derivative of the denominator, which is 3x squared. So if you apply the rule, you will get this derivative, and then you have to expand the brackets in the numerator and collect the like terms. Finally, you will get this final answer. So here we have different rules. At the beginning, you might have difficulties in using the rules, but if you solve more questions, you will get used to them and you will remember them, and you will find that it's easy to use these differentiation rules. Here we have the second and higher order derivatives. If y equals f of x is a differentiable function, then its derivative, f prime of x, is also a function. And if f prime is also differentiable, then we can differentiate f prime to get a new function of x denoted by f double prime. So f double prime is the derivative of the derivative of f. The function f double prime is called the second derivative of f because it's the derivative of the first derivative. So it's written in several ways. F double prime of x, we can write it in this way: d square y by dx squared. Or we can write it as d by dx of the function d by dx. Or we can write it dy prime by dx, or y double prime, or d square f of x, or dx square f of x. So all these notations are used to denote the second derivative of the function. So if you see any of these notation, it means the second derivative of the function. As an example, if y equals x to the power 6, then its first derivative is 6 times x to the power 5. Now, if you want to differentiate one more time, then y double prime will be the derivative of the function, means dy prime by dx, which is the derivative of 6x to the power of 5, which is 5 times 6, 30, 30 times x to the power of 4. So the second derivative of the function is 30 times x to the power of 4. This is the way we find the second derivative. If you differentiate this second derivative one more time, you will get the third derivative, and one more time the fourth derivative, and so on. So there are some functions that you can continue in differentiating it, sometimes unlimited time, sometimes until you reach to a zero value. Like this example, y equals x to the power of 3 minus 3x squared plus 2. Always the polynomial function can be differentiated many times. So the first derivative of this function will be 3x squared minus 6x. The second derivative will be 6x minus 6. The third derivative will be 6, and the fourth derivative will be 0. So this function has derivatives of all orders. The fifth and later derivatives are all being 0. Because if you keep differentiating, you will get 0. So you have to stop here. And this is applicable, in fact, to all polynomial functions. So all these rules have to be used in finding the differentiation of the function. Now here in this slide, we have some questions from your textbook, and we can apply the differentiation rules to solve all these equations. So I will stop here, and then in our class we might attempt some of these questions, and you can solve the rest of them at home. So that's it for today, and Assalamu alaikum. Bye-bye.